All right, so this is the big concept for this unit, looking at collisions, specifically inelastic and elastic collisions. These two types of collisions are talking about the momentum and the energy. So in all collisions, actually in all cases, always, momentum is conserved. However, depending on the way you define your system, momentum may or may not be conserved on a limited scope. But if you broaden your scope, momentum is always conserved. But mechanical energy is not always conserved. Sometimes that mechanical energy gets converted into like heat energy or something. So the total energy is still conserved, but the mechanical energy is not. So, two things could be moving at the beginning, they crash into each other and they stop. So their energy, their kinetic energy, obviously is no longer conserved. So this is an approach that we're going to be using this year quite a bit. So I'm going to start off by defining elastic and inelastic. All right, so we've got three different cases here. Elastic, where energy is fully conserved. All energy, mechanical energy, stays the same. So you add up the kinetic energy of all the objects, it's equal to the kinetic energy of all the objects at the beginning. In an inelastic collision, that is not the case. And just to be fair, elastic collisions don't exist. Unless you're talking about like atomic particles hitting each other, energy is always going to be lost. In the case of like sound, when things collide into one another. This is an idealized situation, but we are going to use it quite a bit throughout the unit because it's helpful for a lot of times. If we look at this, energy is not conserved. This would be for an inelastic collision. This is when two things hit each other and they lose energy. This is the most common thing. Often when an object is deformed, it will lose energy because it will, in a crash. I mean, that's really the point of like, airbags and crumple zones in cars, is that it's removing some of that energy and using it up in the deformation of the vehicle. And then the last one is a fully inelastic collision, which is when two objects collide and they stick together, or multiple objects collide and they stick together. All of these situations, the change in momentum is zero, but there is going to be a change in energy that's different, and you're going to account for it differently. So for this one, the sort of secret about this one is that the final velocities are all equal. For this one, there's not really anything that we know about it. The only thing that we know is that the total momentum it doesn't change. And that's true for all the rest of them as well. And for this one, we know that delta KE, the kinetic energy, does not change. And so for all of these situations, the change in momentum, this is talking about in the instant of the collision, right before to right after the momentum is conserved. Once the collision is over, then we'll go back to using a different method like energy or forces or kinematics to figure out what happens to the object. We use momentum specifically when we know about a collision, and we use it only during the collision, when we're using the collision model for momentum, the multiple object model for momentum. So these are sort of the big basic ideas here. I'm going to take a look at a couple examples, or well, just a short example quickly, and then we'll move on. All right, so for this example, we've got here two masses. We'll call this little m here. It's going to be moving. Big M is going to be stationary at the beginning. So this has an initial velocity, we'll call it of just V0. This one would have an initial velocity, we sometimes call it V02, but in this case it's going to be equal to 0, so I'm not going to define it as a variable in this case. This is moving along, it's going to collide into this block, and something's going to happen. For this problem, I'm going to assume that it's a frictionless surface that these objects are on to begin with. So let's start off by looking at this as if it was a perfectly inelastic collision. These ones are usually the easiest and the ones that you'll come across the most often in problems because they take the least time to do. So basically what we know is at the beginning, the total momentum is going to be equal to little m V0. And this is going to be equal to the final momentum, which for this object is going to be big M plus little m, because they're stick together and they're going to slide together. And since they're sliding together, we can just assume it's one object with a new mass of little m plus big M times Vf. So in this case, what we do is we solve for Vf. Basically, we get the original mass divided by the final mass, all times the initial velocity at the beginning. And so this is basically saying, in all of these situations, what you do is you take the total momentum at the beginning and divide by the total mass at the end, and that will tell you the final velocity that the object moves at the end. You can do it just by setting this equation up. If you also had an initial velocity for the other object, that would just come over here, and it wouldn't be much more complicated to do it that way. Then you're just dividing by this to get your expression for the final velocity. Now, if you wanted to look at the kinetic energy, since at the beginning this would be 1/2 mv squared, and then at the end it's 1/2 m, and this mass has increased for the object overall, which would make the velocity go down by the similar factor. And since it's v squared, you actually wind up with less energy at the end. If you actually write it out, you'll see you have less energy at the end than you had at the beginning. Now let's take a look at this as if it were perfectly elastic. Okay, so if this is an elastic collision, these are going to bounce off of one another. This is going to be traveling that way. It's going to bounce back in this direction. So what we're going to wind up with is big M going to the right, little m going to the left as they bounce off of one another. You don't actually need to know the directions. Depending on the situation, they might both be moving in the same direction. If little m was more massive than big M, they would both be moving to the right. Because it's smaller, it's going to bounce back to the left in this particular case. So we can take a quick look at that here, and the way that we would set this up by showing the conservation of momentum equation to start with. So here we go. We've got that the initial momentum is equal to the total final momentum. And here I've written these both as positive, even though I know that this little mass is going to be going to the left, because this is going to be a negative velocity the way that we write it down in our equation. So in this situation, we have numbers that we know here, as well as two unknowns. One equation, two unknowns isn't going to cut it. We would either need to know the final velocities of one of the masses or use something else. And the something else we're going to use is that the energy is conserved. The total kinetic energy is conserved in this collision. Just like this. And I know this is not the most fun equation to look at, solving this system of equations, but it's certainly doable. You just solve for one of these, plug it into the other one, whatever method you like to use for your systems of equations, that's the one that I would suggest that you go with here. It gets a little bit messy, but it is certainly a doable project at this point. These ones are often not done on the AP test because they just take a little while to do. There are a couple specific situations that we'll get into in class, specific cases, and for those you may be expected to know what happens in those. But for a general case with two unknown masses, it is quite a bit of work to get the answers, so you'll have to do a little bit of that in the homework. Now we'll pull up the last occasion, which is a real collision, also sometimes called an inelastic collision. Not a perfectly inelastic or fully inelastic collision, where they hit each other, they bounce off, but energy is lost as well. And so in the case of a real collision, meaning like real world where energy is lost but they don't stick together, this is what's the most common kind of collision. This equation still works, but we have no second equation. So it is not possible to solve for these final velocities without knowing more information about the system. They would have to tell you what the final velocity of one of them is, or something like that, for you to be able to figure out the other one. That might be a question you could be expected to see at some point, where they would tell you how fast one of the two objects is going at the end. All right, so far we have looked at these collisions in one dimension. We're now going to upgrade a little bit and go to 2 dimensions and think about what exactly that means. All right, so for 2 dimensions, we've got here an object M1 moving towards an object M2, and they're going to collide and glance off of one another. And so we'll probably get something where like M2 will start going off this direction, and M1 will go off in this direction, something like that. So we'll have X and Y components of each of these. So now what we have is our conservation of momentum. You can either do it as one equation with vectors, or you do it as 2 different equations, one for the X components, one for the Y components. And that's the way that I'm going to do this. So let's say here my initial velocity is not perfectly horizontal, so it's got some sort of vertical component to it. You can look at it that way, or you can look at it differently. However you really feel like doing it is fine. But I'm going to just start writing some things out. So for an object where m2 is not moving at the beginning, this is basically your equations that you would use. And I again, don't like memorize these. Just think, what's the momentum at the beginning? What's the momentum at the end? I want to put in x components and the y components. That's all that I'm doing here, saying this object is moving, and then at the end, these two objects are moving. So I'm just adding up their momentums. And so in this case, this would be sort of the way that this approach would work out. If this was a perfectly elastic collision as well, we would add in the last equation, which ignores direction and is the same one that we had before, where that's 1/2 mv squared initial for the first object, plus 1/2 mv squared for the first object at the end, plus 1/2 mv squared for the second object at the end. We could write that out as well and use those three equations to find our three different unknowns in this case, or several different unknowns in this case. And so that's a method that we can use to solve these kinds of questions. One thing to pay attention to, though, let's say if this was perfectly horizontal at the beginning, that would mean that this initial y velocity would be 0. And this is kind of a special case you might come across where it has no momentum in one dimension, or you could just set up your coordinate system so that there is no momentum in one direction. And then what that tells you is that these two final momenta are going to be equal to one another. They're equal and opposite. So one would be pointing up, one would be pointing down. Basically would tell you that the y components of these momentums are going to cancel each other out. And so that sort of is an extra equation that you can use to help yourself solve these kinds of problems as you see them. All right, well, that's sort of the big overview for this. And you're going to be applying these concepts to some problems in class over the next week or two. So let me know if you have any questions about any of this material or any of the problems that you see online. Thanks, and we'll see you in class.